A unit vector is defined as a vector that has a magnitude of unity with no units. In Cartesian coordinates, there are three unit vectors: I hat, which lies along the x-axis, j hat lies along the y-axis, and z k hat lies along the z-axis. These three unit vectors are perpendicular to each other, and each has a magnitude of unity. Each vector in one dimension has only one component that represents the magnitude of that vector, but its direction may be referred to using the unit vector along the considered axis along which the vector lies. A vector along the x-axis, for example, is written in terms of a unit vector I hat as follows, where the component A on the x-axis ax will represent, in this case, the whole magnitude of the vector. The I hat refers to the direction of the vector along the positive x-axis. However, the magnitude of the vector, if it is given 3 units, then the vector will be represented as follows. However, if the vector is drawn along the x-axis in the negative x direction, in such case, it is represented by its direction and magnitude, where the magnitude is given 3 units and I hat having a negative sign refers to the direction along the negative x-axis or to the west. What about if the vector is along the y-axis? In such case, it has a 0x component, and it's drawn like this, and if the magnitude of the y component has 3 units, then the vector is written as d equal 3j hat, where j hat as positive refers to the direction along the positive y-axis. If the vector is directed downwards or to the south, then in this case it's drawn like this, and the vector has a magnitude of 3 units along the y-axis, where the negative j hat will refer to the direction due to south or to the negative y-axis. In 2 dimensions, a vector is represented in terms of 2 unit vectors and 2 components. For example, if the vector is drawn in the xy plane, it can be written in terms of the unit vectors I hat and j hat, and it has 2 components, ax and ay, and the vector is written as follows. Now, the x component can be found by projecting a line from the head of the vector down to the positive x-axis, while the other component, the y component, similarly can be drawn by projecting a line, by this time from the head of the vector to the y-axis. And here we are, this is a y. You see, these 2 components are drawn now in the first quadrant, where the angle theta is positive, and it's drawn with respect to the positive x-axis in the counterclockwise direction. This angle, of course, subtends the image of the y component, and then this triangle, in such case, is formed from these two components and the magnitude of the vector, which is a right angle triangle. When the vector in xy plane becomes in the second quadrant, the vector may have a magnitude of 1 unit and an angle of, for instance, 120 degrees. In such case, how can we find the vector b? Well, the vector b can be written as this in terms of I hat and j hat, where here the x component is considered in the negative x-axis and the sign negative is embedded in in the unit vector I. Now, how can you find the components bx and by? Well, there is an easy way to do that. If you consider the right angled triangle whose sides are the x component and the y component, in addition to the hypotenuse, which represents the magnitude of the vector. This right angled triangle will have an angle phi, and this phi is an absolute angle. So to find the x component, what you do is just to multiply the magnitude of b, which is 1, by cosine the angle, which is going to be 60 degrees. Then, in this case, you will get bx equals 0.5 units. However, the x component is obtained, can be substituted right away in here. So you will have just that. The minus sign is there, 0.5 unit, then I hat. Now, how can you find the other component, the y component? The y component is simply the product of b by sine the angle 60, sine phi, which is 60. Then you're going to have 1 multiplied by sine 60, which is 0.86. So, unit. So in such case, this value is going to be substituted in here. Then you have the answer is minus 0.5 I hat plus 0.86 j hat. Alternatively, you can use this angle theta instead of phi, but in such case, you have to drop the negative sign here. The reason is because having the cosine of 120 is equivalent to the cosine of 60, but cosine 120 will give you a negative sign, so you do need to write the negative sign twice, and you will get the same answer. What about if the vector becomes in the third quadrant of the xy plane? Here, the vector c is drawn in the third quadrant where its direction theta is positive, as it's drawn with respect in the counterclockwise direction with respect to the positive x-axis. Now the vector c has two components, cx and cy, are directed towards the negative x-axis and y-axis respectively. So how can we find a final answer for C if, for instance, the vector C is given a magnitude equals 1 unit for simplicity, while its angle theta is given as 240 degrees? Well, to do that, there is an easy way of doing this. As we mentioned before, we have to choose a right angle triangle where the hypotenuse of this right angle triangle is going to be the magnitude of the vector C. However, its other two sides are the x and y components of the vector. In this right angle triangle, we choose an absolute angle phi, which can be found if we subtract 240 for the given angle minus 180 minus 180 for this angle, then the answer is 60 degrees. Now, to find the magnitude of the x component from this information, you just apply the trigonometric relation. The adjacent of any right angle triangle to the angle phi, the adjacent to the angle phi in the right angle triangle, is simply the product of the hypotenuse, which is 1 here, and cosine the angle, which is 60, which is 60 degrees. Then the answer is simply 0.5. So in such case, the magnitude of the x component must be substituted there. Now for the y component, again applying the trigonometric relations for this component, which is equal to the magnitude of the x component is equal to hypotenuse, the magnitude of the hypotenuse multiplied by sine the angle, which is 60, multiplied by sine 60. And then the answer here is 0.86, 0.86. And then you have to substitute this into here the magnitude of the y component. The final answer in such case here equals to, if you just write the minus sign down here as is, and then the x component 0.5. Now this 0.5 obviously accompanied with the I hat, and then you just drop again down the minus sign for the y component, and where its magnitude as found by 0.86, then with j hat. And here we are. We got the final answer, final representation of the vector in terms of I hat and j hat. Next, an animation will be shown that represents the change occurring in the components of a vector as this vector changes its direction.
We'll use this animated vector arrow to show how a vector can be broken down into components and how those components vary as the angle of the vector changes. This vector can be broken down into two components, one along the x-axis and one along the y-axis. Here's how the components change as the vector is rotated around the origin.
This example is an application for finding the components of a vector. In part A, we are asked to find the x and y component of a vector of magnitude 5 meters with an angle of 37 with respect to the positive x-axis in the counterclockwise direction. And the same magnitude of the vector, but drawn in the fourth quadrant with an angle 37 degrees in a clockwise direction. And again, the x and y components are needed to be determined. Well, let's review the information given in part A of the problem. The vector A has a magnitude of 5 meters with an angle theta as shown in the drawn diagram. The vector actually has an angle 37 degrees north of east as shown in the direction of right there. Now let's consider the right angled triangle whose hypotenuse is the magnitude of the vector A as mentioned before, and then its other sides, the x component and the y component. To find the x component, write the trigonometric relation for cosine theta as adjacent side, which is ax in this case, over the hypotenuse sides, which is the magnitude of A. Then the x component is going to be the product of the magnitude of the vector 5 multiplied by the cosine 37, and the answer is 4 meters. For the y component, sine theta is used, which is equal to opposite side ay over the hypotenuse side A. And then ay is the product of the magnitude of the hypotenuse, which is 5 meters in this case, multiplied by sine the angle theta, and the answer is this. Now the final answer can be written in two ways, either A equal 4 I hat plus 3 j hat, or the vector A can be written as the numbers between two parentheses 4 and 3. 4 for the x component and 3 for the y component. Now in the second part of this example, the magnitude of the vector D is given as 5 meters with an angle phi minus 37 degrees. Of course, the vector is 37 degrees below the negative x-axis, or 37 degrees is called south of east. If you want to find the positive angle of this vector with respect to the positive x-axis in the counterclockwise direction, then all you to do, you just subtract 360 minus 5 to get 323 degrees. Now it's obvious that the vector in the fourth quadrant has two components, the one positive on the x along the x-axis, and the other is the y along the y-axis, which is negative. So we choose the right angled triangle as before, but this time in the fourth quadrant, where the hypotenuse represents the magnitude of the vector D, and the angle phi is chosen between the adjacent side and the hypotenuse. To find the x component following the trigonometric relation cosine theta, which says that the adjacent side dx over the hypotenuse side d gives us the x component, which is the multiplication of the hypotenuse and cosine theta. if we substitute 5 meters for the magnitude of the hypotenuse and cosine 323 for the angle theta, then we'll get the answer which is equal to that. If we substitute the angle phi instead of theta, phi of minus 37 degree, obviously both angles phi and theta will give the same answer, 4 meters. For the y component, we apply the sine theta relation, which says that the opposite side dy over the hypotenuse side d. This relation gives us the y component, which is the product of the magnitude of the d vector, 5 meters, multiplied by sine the angle theta, 323. Or alternatively, we can choose sine phi instead, where phi is substituted minus 37 degrees. In both cases, the answer is minus 3. As expected, the two components, one of the components along the positive axis turns out to be positive, while the other component is the negative, which is the y component. And then the vector can be written as in both ways, as shown before. Now, another application for the components of a vector is in this problem. A vector has an x component of minus 25 units and a y component of 40 units. Find the magnitude and direction of this vector. To solve this problem, we have to start drawing the x component of magnitude of 25 units and direct it towards the west. That's why the negative sign is there. And the y component is directed towards the positive y-axis with 40 units. Next, write an expression for the vector having its x and y components in terms of I hat and j hat. And writing down 25 units for the magnitude of the x component with a negative sign that refers to the west, and then 40 units for the magnitude of the y component with a positive sign which refers to the positive y-axis or to the north. The next step is to draw a right-angled triangle in the second quadrant as long as the two components are there. So this right-angled triangle has two sides, one that's for the x component and one for the y component, while the hypotenuse represents the magnitude of the vector wanted to be determined here. Now we'll choose an angle phi, here drawn in clockwise direction. It may refer to the direction of the vector with respect to the negative x-axis in a clockwise direction. Now, first, let's determine the magnitude of the vector using Pythagorean theorem. R equal square root of x squared plus y squared. Write down the values of x and y, and then the answer is 47.17 units. Now we can draw the vector of that magnitude of units in the diagram. To find the direction, let's find the angle phi by using tan phi, which is equal y over x. Y given a number or a value of 40, while x given a value of minus 25. Now phi is the tan inverse of this ratio, which turns out to be minus 58. The minus sign or this angle refers to the clockwise direction with respect to the negative x-axis. Well, the direction of any vector is usually written with respect to the positive x-axis, and the angle found in the clockwise, counterclockwise direction, we'll call it theta, is must be equal to 180 minus phi, the obtained angle of 58 degrees. So the answer to the angle theta is 122, and again this angle is drawn from the positive x-axis in the counterclockwise direction with a magnitude of 122 degrees. How can we write an expression for the vector in 3 dimensions? Well, in XYZ coordinate system, for example, a vector A may be expressed in terms of the 3 unit vectors I hat, j hat, and k hat. This vector has 3 components, ax, ay, and az, as the diagram shows that this vector A is broken into these 3 components. How can we determine the magnitude of this vector? Well, the magnitude of this vector can be found by taking the square of A plus the square of ay, taking the square of ax plus the square of ay plus the square of az, and then take the square root, and this gives you the magnitude of A. Now, the student may ask, what about alpha, beta, and gamma? Well, alpha is the angle between the x component of A and the vector, while beta is the angle between the y component and the vector. And finally, gamma is the angle between the z component of the vector and the vector. Now, how can we determine these angles? Well, you can determine these angles simply by projecting a line from the head of the vector along the x-axis to make a right angle triangle which has 2 sides, ax and the magnitude of A. So apply the trigonometric relation for cosine alpha, which is equal to ax over the magnitude of A. From here you can find the angle alpha, which is the cosine inverse. Similarly, to determine the angle beta, project another line from the head of the vector perpendicular to the y-axis. Again, you have a right angle triangle. Here cosine beta equal to ay over the magnitude of A, and from here you can determine beta. In the same way, alpha can be obtained by using cosine alpha equal az over the magnitude of A, and the value of gamma can be obtained directly. Regarding the vector in 3 dimensions and its corresponding components, the student is asked to solve this exercise. A vector is given by r equals 2I hat plus j hat plus 3k hat. Find part A, the magnitude of the x, y, and z component. Part B, find the magnitude of the vector r. And then part C, determine the angles between the vector r and the x, y, and z axis. For part A, the x component is just plus 2. The y component is plus 1. And the z component is plus 3. For part B, To find the magnitude of the vector r, this is simply equal to the square root of the square of the x component, which is 2 squared, plus the square of the x component, which is plus the square of the z component, and this is simply square root of 14, and the answer is 3.74. Now determine the angle between the r vector and the x component, which has an angle named theta x. Apply the cosine identity, cosine theta x. Here it's equal to the adjacent, which is x, divided by the hypotenuse, which is the magnitude of the vector r. The x component has a magnitude of 2, where the magnitude of r is obtained just right now as 3.74. From here, you can get theta x equals to the cosine inverse of this ratio, 2 divided by 3.75, and the angle then will be just written straightforward. While for the second angle, theta sub y, which is the angle between the vector r and the y component, again apply the same identity, cosine, which is the adjacent, and in this case the adjacent is y, divided by the hypotenuse, which is the magnitude of the vector r, and substitute the values, 1 for y and 3.74 for the magnitude of the vector r, and then from here the angle theta y is the cosine inverse of the ratio 1 over 3.74. Here the answer for theta x is 57.7 and for theta y is 74.5. And you can follow the same way to obtain the angle between the vector r and the z axis, which is going to be 36.7. This is a simple test to understanding of the students for vectors and its component. The question here, what is the y component of the vector 3i hat minus 10k hat meters per second? Is it 3 meters per second, or minus 10 meters per second, 0, 10 meters per second, or none of those answer? Well, the vector here is written in the xz plane, where it's obvious that the j hat is not there, so the y component is 0. Now a second objective question. What is the magnitude of the vector d, which is equal to 10i hat minus 10k hat meter per second? The answer is it's 0, 10 meter per second, minus 10 meter per second, 10, or 14.1. Well, the vector here is in the xz plane, and it has a magnitude of the square root of the square of this vector, the square of this component, plus the square of this component, which turns out to be 14.1. The next slide, an animation, will be demonstrating the representation of a vector in 3 dimensions, and how does this representation change as you look at the vector through one of the perpendicular axes.
This metal frame is a model of a three-dimensional coordinate system with x, y, and z axes. A vector that is anchored at the origin is free to move in the volume defined by the three axes. We'll move it to different positions in the frame and look at the model along each of the three axes to show the components of the vector on those axes. When we look along the z-axis, we see the components of the vector in the x and y axes. Looking along the y-axis shows the components along the x and z axes. Looking along the x-axis shows the components along the y and z axes. Now we'll change the position of the vector in the frame and repeat the sequence.